great pleasure to introduce Professor Luigi Carro, who received his master and PhD degrees from Universidade Federal do Rio Grande do Sul, Porto Alegre, Brazil. Professor Carro is currently with the Applied Informatics Department at the Informatics Institute of the same university, being in charge of computer architecture and organization. Before his PhD, he was also working in ST Microelectronics in Italy. And Professor Carro has wide expertise on computing systems ranging from embedded systems, digital signal processing, and VLSI design. He has authored several books. In 2001, Digital Systems Design and Prototyping. He co-authored Fault Tolerance Techniques for SRAM-based FPGAs in 2006, Dynamically Configurable Architectures and Transparent Optimization Techniques in 2010, and Adaptive Systems in 2012. In 2007, he received the Flowers Research of the Year in Computer Science Prize. And we all know that Professor Carro is an active member in SAMOS community. He was SAMOS General Chair in 2015, Tutorial Chair in 2014, Program Chair in 2011. And we know Luigi as a lively person who is always willing to discuss new research ideas and looking for research collaboration. And today he's sharing his thoughts on processor memory bandwidth problem in data-centric applications. And the topic is here. I'm looking forward to entertaining, interesting keynote. Thank you, George.
Thanks, Jan, for the kind introduction. Different from the previous presentation, this one I understand something about, so we can really make questions at the end. Of course, if there are too much complicated questions, I'll blame the students and ask you to contact them. But anyway, this talk is a work of Paulo César, who is my PhD student. João Paulo and Rafael are master students, and Antonio is a colleague who works on the same field. So I chose this title because I wanted to attract your attention, at least in the beginning, and then later you can pick up your phones and send emails and WhatsApp messages that everybody does. So why is this title interesting? So let's take a machine gun, and let's imagine that it shoots 1,000 bullets per second. So no real machine gun can do that, but just think about it. So 1 second, 1,000 bullets gone. And this is great, I mean, from a machine gun perspective. Now that brings a problem. Who's providing the bullets? Where are the bullets coming from? Because the next second, you need another 1,000 bullets to shoot. So that's what's providing the bullets. Big, heavy, and slow truck, full of bullets for the machine gun. Pretty much you have guessed the analogy. This is exactly what's happening now. We do need data which is stored on memory, and everybody's familiar with this graphic. And this is a reproduction of some Intel historical data. This is speed up normalized to 2008. As you can notice, we know that memories get bigger but not faster. And of course, lots of people have worked on this for a long time now, since the beginning actually, on building the memory hierarchy. Another complication that's come is the memory wall, and of course the end of the NARD scaling, so really you cannot push things around anymore. And everybody here is familiar with this. I'm not going to stress too much. Now, that's the plot I want to discuss with you now. I've been told that the color was bad ideas, but bear with me the following. This light blue here, this blue at the bottom, is the amount of time you spend in CPU. So this is time. That's the 100% the execution time of several different algorithms. These algorithms are taken from Polybench, and they represent several different applications. So very simple data structures and some machine learning, for example, correlation. Then a whole bunch of linear equations, and that linear solvers and matrix manipulation and full matrix manipulation. And then some flow problems that can also be related to graph problems, and stencil, which have some locality. So in this blue here, here, you can see it's the time spent in the CPU. So basically, it's the time spent in the machine time. And we have spent several years and conference and PhDs developing very efficient machine guns, developing processors, which is great. However, you notice that any further improvement in processors is going to be ineffective, because in the average, only 10% of your time is spent in the processor. All the rest of the time is spent bringing data to the processor. Let's take, for example, correlation. If you want to do some machine learning, you'll notice that the time spent in L3 serving is huge, and the time in disk and memory serving is also the dominant factor. Of course, for some algorithms, you still have caches are very useful. This example here is about Puppet's manipulation of matrices. So pretty much you're taking a single matrix and moving things around. There's a lot of locality. You can use memory tiling, and then caches are very effective. But if you think about the money you spend in the memory hierarchy, you see that it's not really effective for the kind of application we are looking at right now. I'm talking about machine learning application. I'm talking about recommendation systems. I'm talking about data which is being transformed from a massive parallel, let's say pixels, and then it's moving on to some decision. It's a cat, it's a dog, or something like that. So clearly something must be done. And what people have been doing is saying, okay, this memory gap here, I'm going to provide bandwidth. I'm going to spend money. I'm going to put more resources into bandwidth. And hopefully, we are going to bring this memory speed up to date. So our view is that money is not the only problem, right? I mean, it's not only about energy, it's not only about increasing resources. It's, can we do this in an intelligent fashion? Can we do this in a way that we save energy? Can we really bring this higher bandwidth to our benefit without just spending money on it? And that's the purpose of this talk, right? So this is the main message, and of course, I'm trying to prove now during this next minutes that yes, there's something to be done that requires intelligence and can be adaptive to the kind of need of the application. So basically what I'm going to talk is what kind of technology you're going to use to provide this new memory behavior. And then we're going to talk a little bit about our competitors, what other people are doing around in the world. And then I'm going to stress our approach to near memory computation in the sense that how can you embed intelligence in this kind of devices so that you can cope with several different applications. And also I'm going to do a detailed comparison on area and performance and power of other published work or recently published work in the same field. So, what's happening is that in the past few years we have the 3D stacked DRAMs are commercial, and that's very interesting. They have a whole set of problems like temperature dissipation, reliability, but you see already products that you can buy at the corner that have this kind of technology. This technology is already in. And basically what these guys are providing us is bandwidth. So this is sort of a representation of this high-density memory. You have layers of memory DRAM chips, and several DRAMs are placed in each one of these containers here. And they communicate using true silicon vias up to this. Now the novelty here is that it's not only about DRAMs. Since it's 3D technology, you can pretty much choose whatever you want to put inside the 3D stack. And one of the ideas is to, and this is fabricated like this, you have a layer here where you have a regular CMOS process for switches. So the beauty of this is that you have a massive amount of data, a massive amount of parallels bandwidth to reach this data, and you have a layer here that you can use for whatever purpose you want. Analog devices or fully digital microprocessor, whatever switches, whatever you want, it's a regular CMOS process. A very interesting aspect is that the people who are selling this are already providing instructions. For example, HMC gives you the memory and provides you with an instruction set. You can, for example, read from a position in memory, add a byte, and write it back to where it belongs. So that's something the processor can tell the memory, do this for me, please, and the memory is going to do it without processor intervention, of reading, coming to the several layers of caches, and then reaching the register bank, and then coming back all the way. So that's a concept which is already there. And when we started this research, we wanted to say, how can you better use this kind of technology? So that's what I just said, without animations. Yeah, one interesting aspect that we noticed that most people would, this layer here is some sort of prefix. You have some predefined operations that you can do. And basically it's character manipulation, 8-bit manipulation, byte manipulations. Now, one important aspect is that if you look at the technology that these guys are using, you have some limits. The first limit is the following. For different years, you have a certain capacity in gigabytes of the total memory for different technologies, and the number of layers which are available. Also, technology for the true silicon vias defines the number of volts that each one of these columns here, and that pretty much settles the amount of parallelism that you might have. Now, another interesting aspect is that if you take the area of these devices overall, you have a certain area per volt. That means how much space you have to fit things that you can take extra benefits. For example, a certain connection here, a certain true silicon vias, can provide you with a number of bits, very high number of bits for seconds. And then anything you do to exploit the parallelism cannot expand beyond this area here. Because if it does expand, that means that you're not going to use the full parallelism available by the memory. Another very important constraint is power. So there's a huge discussion, see how much power can you really extract from these devices? Can you really feed the device and then make it run faster pace? Well, some people say, well, the total amount of power that you are allowed to have is around 11 watts for the whole stack plus the layer here. And we are not in the technology business, we are just reading papers about it. So it's a discussion. Some other people say, no, listen, you can say that just for the logic layer, you are allowed to expand 8.5 watts. So I don't know who's going to win this discussion, but let's say there's a power limit because you have to extract temperature from this complex device. So there is a power limit. Let's try to live with that. Now, there are some applications that are limiting, because, for example, if you take several versions of GPUs, you have a huge bandwidth and capacity of processing. However, if you are using a memory for example, matrix multiplication here, you end up with a normal memory bandwidth. The effective bandwidth of gigaflops per second that you can actually process is much smaller. So in this situation here, you're seeing that the memory bandwidth is limiting your application. The effective bandwidth then is much smaller. So locality is not enough to provide you with to feed all this processing power over here. On the other hand, you may also have benchmarks where you don't have enough processors. So the memory bandwidth is huge, but you don't have enough resources to take benefit of this memory. A classical example is, for example, MapReduce kernels. So it ends up that, for example, you put a huge amount of cores which have a peak bandwidth of only 3.4 terabytes, which is okay. However, if you look at the memory, with 32 HMCs, your memory bandwidth is much bigger. So, from an energy perspective, what you want to do is to correctly match the amount of memory bandwidth with the amount of processing power. Any mismatch is going to represent inefficiency, either in terms of performance or in terms of power. And of course, the more you can delegate the memory itself, the better, because then you don't spend energy moving things around. And most important, you don't spend time moving things around, as in that slide that I mentioned before, where most of your time is spent just transferring data. So let's take a look of what people are thinking about, and I selected basically two projects which have very recent results and which are very interesting by themselves. The first is the next project. So the whole idea here is the following. They say, look, there are going to be new technologies, new nano stuff, and the way to build these new things is to build on top of traditional CMOS. So on top of traditional CMOS, let's build up some specialized memories using memory stores, nanotubes, whatever, because that will help in power dissipation, because power of these nano devices is much smaller, and that will help in reliability. And they have several papers that are shown here, and you can see that they prove the effectiveness of their approach. And instead of I'm going to this picture here, you can see that pretty much for each layer they are sort of working with different solutions on different ways of propagating data in the stack. Now, the main drawback here are two, that, in the sense that this new technology is yet not reliable and yet not reaching the performance level of CMOS, and, but they have built some proof of concepts too. In this paper of Colders, they report some huge speed up of ADP benefits of their system against the classical 2D baseline. So that's pretty much the benefit of having a 3D version of a 2D processing power. And another, smarter thing. One thing I want to call your attention is that they're trying to, for different pink situations here, that's some extra memories that they are inserting on this 3D data structure. So you have a 3D data structure, but you use specialized custom memories designed to solve the problem at hand. So it's very good as an accelerator, but you cannot use it for general purpose processing. Yeah, okay, more data, I'm going to skip this. Another nice cooperation is the CRISP project. The CRISP project, they're really not looking at using a huge amount of new technologies, nanotubes, and they limit themselves to memory resources, for example, but rather they do a very interesting idea of specializing their memories with some added hardware so that the memory takes some responsibility for some tasks. And I guess that kind of picture that shows, it's complicated and I fully don't understand, I have to ask my student about this, but the important thing, if you look, if you look here at the glossary, the blue aspects are add-on hardware. So this is add-on hardware that they put on top of the memory so that you can provide extra processing for a specialized task. And I guess the best example they have here is, for example, DNA sequencing. They are using 3D, and each one of these memories specialized on pattern matching for a certain DNA thing, whatever. So, yeah, they are perfect too. Let's take a look at what they are providing and what are the bottlenecks. So in the next project, you have an end-to-end team design organization, meaning that you switch your whole stack and you make changes on each layer of the stack to provide with a solution. Now, for the CRISP project, they decided to add ASICs together with memory, so sort of a more traditional design, but still specializes for a single task. Both are sort of technology dependent. Some of them rely on technologies which are not yet commercial, but most important from our perspective is that programmability. I mean, how can the regular Joe programmer, the Mickey Mouse programmer as Yale would call him, use these devices? And the answer is he can't. I mean, there's no way that a regular guy can write a C code to take benefit of these extra layers, of these extra resources. And that for us is a killing thing. We need approaches where we can sustain the software stack. So the software guys are going up and up. They are inventing, I don't know, Scala, which is a virtual machine on top of a Java machine, which is itself a virtual machine. So it's completely out of the hardware space. How can you speed up things like this? How can you sustain software productivity in this new scenario? So let's take a look then of our approach and what you think we can do about this kind of things. So first, let me give you a brief ideas of the simulation environment we developed. We said we must keep on software development. So whatever we do, the programmer must not suffer. He must not go too far away from what he's used to. So we decided, let's use LLVM. Whatever language you choose that can generate LLVM intermediate representation is good. Moreover, I don't want to do Pragma. I just want regular C code. Every time you use Pragma, you're asking the programmer, you have to think about. And we know software guys don't like to think. It's a joke, okay? If you're a software guy, don't get offended. But of course, I think they like to think on their specific problems. They don't want to worry about what's the hardware doing, how can they do things. Yeah? So no problems. So we are able to generate vectorized code. That's very important because you really want to increase productivity. Another aspect is that we want to simulate things. Since we don't have this extra hardware, we want to make sure that whatever we think of as a processing memory device or processing near memory device, is it better than the other option? So we need a simulation environment, and then we picked up Gen 5. I'm sorry? We picked up Gen 5 because this way we could distribute things and everybody can try their own version of this processing memory device. And as long as you have simulation capabilities, a lot of machines, you can really wait for the simulation to run in 2 days, something like this. It's not quite fast, but it gives an idea. One important thing that I forgot, I'll go into details later. So how we proceed. Let's take a very stupid example of vector initialization. Pretty much all you have to do is store this constant into some array. So if you compile it to Intel code using AVX 512, that's a vector machine, so that's the best comparison you might have with a current microprocessor that can do vector manipulation. And it will issue several different instructions, and of course here in orange you can see the jumping that you have to cover the whole size of n. In our version, with our pin compiler, we generate some sort of using the same arithmetic instructions, but rather with huge vectors. And hidden here in these two instructions, the same broadcast instruction here, you see here, that's something that we set everything, and then we start really updating the vector. So the benefit here is not, how do you say it, it's just about bandwidth. You are just exchanging several small instructions to a big instruction. So not much intelligence required here. Now, hidden in these two small instructions is the communication between the processor and the memory. Somehow you have to say to the hardware which is inside the memory, I need you to do something for me, and when you are finished, let me know it's finished, so I can follow on doing whatever I want to do. And all this communication is hidden in these two instructions here. So the compiler takes care of this communication too. Let's take a little bit more interesting example, which is part of the DXP kernel. And now we're doing something, okay, you're reading something, adding it to another position in memory. So that's a more interesting situation where you have to read the two different pointers and then compose them and store somewhere. Again, the amount of instructions that the current vectorized CPU can do is huge. And remember, this has very low locality. So we are going to have lots of cache misses in the process here. While here, there are no cache misses. You are doing everything inside the memory by specialized hardware. One important aspect that I'm going to talk a little bit later is that the compiler is not only able to take use of the huge bandwidth, but it can fine-grain solutions for this bandwidth so that you are not wasting resources. I'm going to give you more ideas on this later. And here I have some results of what can you do. What's happening here, we have three applications, Stencil and Gem, and these applications have different locality characteristics, temporal and spatial locality. And we are using, the blue is the Intel machine, and then we have two versions of our design, the RView, that's the reconfigurable unit, which 256 and 512 bytes. And here you have the speed up normalized to AVX. So one is always the Intel. And this is the speed up you can achieve by processing in memory. Let's take a look of each one of these examples. In this example here, which you have a huge, remember I showed you the code, basically it's a vectorized, very easily vectorized code with high spatial locality. But of course, no temporal locality. Really much you read an element, you read another one, you add, you write it back. I mean, caches are useless. Moving data to the caches and to the processor to do the addition and then back causes you a loss of performance, and you can gain a lot of performance with this huge amount of vectorized operations. Now, if you go to Stencil, if you remember Stencil, you already have more locality because you compute some, I don't know, pixels, and then this information goes to the cell next to me, down to me, perpendicular to me. So there is some reuse of information which is already being processed. And what's happening now is that although you have more information, you still can benefit from vectorization. For example, the larger RVU here can get a higher speed up. Why? Well, because temporal locality exists, but it's not at its maximum. So it's really not used. Vectorization still can play a bigger role. So the larger the hardware, the better you use the bandwidth. Finally, if you take this example, you notice that what's happening here is that there's much more locality, and still we are changing the size because this is a big array, and somehow we are losing information, losing processing capacity because you have the extra hardware, but the information which is coming off the memory is not using that extra hardware. So there are some gains, but you're not as efficient as before. So the whole idea then is, I forgot to mention, is that we use that layer of switching to introduce our pin. And basically, our pin, the first version of our processing memory device was quite stupid. We pretty much copied Intel hardware. I think I have a figure here. Yes. We sort of copied whatever Intel was using, made a few adaptations and said, let's use this and see what's going on afterwards. And the only novelty here is that we have one pin, one capacity for a volt. So all these guys can work in parallel. And we dimension these guys to make scalar functional units, but also that can handle floating point operations. So pretty much this is the standard design. The first version was the standard design. So then we said, okay, let's synthesize this and see where it leads us. And then synthesizing for 32 nanometers, we get different results of frequency, bandwidth, area, and power. Let me remind you that for the current technology, we have a space constraint. We can spend at most 4.5 square millimeters per volt. But more important, you have a power constraint. So to the limit of 11 watts or 8 watts, whatever, you can set only 530 milliwatts per volt. So if you look at our design, you notice that you can increase the frequency, the bandwidth is increasing and reaching the same bandwidth that HMC can provide. However, the area is okay, it fits inside the volt. That means you have enough space to put the amount of hardware you need. Unfortunately, the power is a problem. This barrier here limits the amount of things, so I cannot run larger RVUs, and I cannot run with a higher frequency because power is limitation. So we need to do something. We have a power consumption that is higher by a factor of 4 from what we really budget. So let's go back to the design and see what we can do, and pretty much we copied these guys here, some ideas from these people that say, let's reconfigure something, let's add intelligence to it so that we can save some power and reuse some hardware. And I have to confess, I don't know the details, but my students do. I can put you in contact with them. But the most important thing is that by adding some intelligence at the lower level, you can really reach a much better compromise now. Notice that for almost all the designs, we are within the power budget. And of course, we are within the area. So that's good news. Now the question is, how are other people doing? Because, besides those guys that I mentioned at the beginning, processing memory is an old idea. I mean, people have been doing this for 20 years now. And what's happening? And some of these people are also moving to 3D stacks, like we are, and they're publishing papers. And we try, how are these guys coping with this area and power constraint? It ends up they are not. And I want to make a comparison with other people. So don't worry about the small things here. I'm going to enhance them. If you need, I can send you some papers where we wrote this. But let's compare a bunch of guys. So first observation is that they are somewhat recent. This is our work. And all the other guys are quite recent, let's put it this way. And these are somewhat older, but within a time window which is doable, let's put it this way. What are we comparing? We're comparing several different architectures and several different organizations. Notice that some of them are from AMD, ARM. This is our reconfigurable vector units. Some have for example, AMD has some sort of GPU, like a massively processing data. And some of them are like the regular processors and have an out-of-order processor over there too. So all these have come from these different publications. And let's say, here is a representative of GPUs. So pretty much we are trying to do some aggressive machine guns being provided so that you can really boost things around. On the other hand, we have these ARM versions, and they're a nice comparison because of the instruction set. And then you have some specialized machines like this BuildW and other machines and ours. So we wanted to check whether what is reported in the paper is feasible. Each one of these guys also has a different technology process, which is a nightmare because it makes the comparison much more difficult. And also the number of volts per device which is being used to feed this device, and the number of cores that you are using. So pretty much some of this information is estimated. We cannot have access to all these details, but it gives us a rough idea on the principle, on the idea of comparison. So what we have to do is, let's scale all designs to 28 nanometers. And of course, we're going to say, yeah, but the scaling, look, let's just look at the big picture and then we'll see how this details of the comparison. So we're going to make all the designs scale to 28 nanometers. All the designs are going to use the same amount of volts because we have to compare apples to apples. And then let's look at the performance they can provide in gigabytes per second and see if they match the performance of HMC. So what we want to do is to see who has the best performance while maintaining the power level that it is required. And here's a nice picture full of colors, but don't worry about who is who modulator. The important thing is the following. Here you have the area, and here you have the max bandwidth. So we notice that some people provide you with bandwidth with not too much area. Some designs consume huge amounts of area, but the bandwidth is limited. And pretty much if you say, oh, I have an area constraint, I am using 32 volts, there's a 4.5 millimeters square millimeters per volt, so that's the amount of area that you have. So some designs are clearly not manufacturable in the current technology that you're using. You cannot put them together. So we can eliminate those. And those are, as expected, for example, GPU-like style. Because of course, you have GPUs, you need a massive amount of processing, so they are not going to fit in the space you have. Some other designs, like the ARMs, are very area efficient. And however, notice that they don't go to the maximum bandwidth. So yes, I can put more processors, but I'm not matching the bandwidth that I need, that the memory is providing. So I'm wasting energy somehow, and I'm losing performance. And this is the ARM Cortex-35, which is a single instruction multiple data machine. So it's a meet in the middle approach. You have some GPU-like instructions, but they are only fixed point, not floating point. And this is our range of designs that we provided, and which are, okay, they have a decent area and they can reach different bandwidths. So this is for area. Let's take a look on power. Now, in this axis you have power consumption in watts, and then again the maximum bandwidth. Remember that all designs have been normalized to 32 volts. As you notice, some designs are very expensive in power, some designs are linear here, but even if you spend power, you don't reach the maximum bandwidth that the memory can provide. Here is, in this green line, you have the power budget of 8.5 watts. So if the total limit of your processing power is 8.5 watts, every design to the right here is forbidden. It's going to dissipate too much. If you put here you notice that the out-of-order core is not using the whole bandwidth, but still is within the budget that we expect, because it's using several volts, so it's not using the full bandwidth, but you can use it because the power is okay. The ARM Cortex, and this is the sequence of RVUs, and this is another RVU. This is the ARM Cortex with single instruction multiple data instructions, so it has lots of bandwidth and it's still within the power budget. This is another version of our design with a higher frequency, and here you have the 11 watt limit. You can see that some other designs come into play. This is us, and this is the Cortex with floating point units. Okay, so putting all these things together, you can see that this is the performance efficiency measuring gigawatts per milliwatt. It ends up that our design is great. Oh yeah, sure. Oh, who is this guy? It's not us. It's the ARM Cortex, single instruction multiple data. So that also shows a way that you can use memory, because now you can put a full processor inside with vectorized instructions. The only caveat is that this guy is not floating point. It's only fixed precision. If you move the area and power of this guy to floating point, what's happening is this. The efficiency goes really down. And what I'm trying to show here is that if you want to use the memory bandwidth, it's not a matter of just put things inside and let them run. Some intelligence is required, because you really want to make the matching between memory bandwidth and hardware utilization. And this is just another aspect. If you say we are normalize everything and extrapolate the number of cores that you need, and let's say our design is number 1, and you can notice that everybody else expends lots of power or lots of power. That's pretty much the same thing I said before. I'm going to skip this. Yeah. So, let me, oh, wow, that was fast. I want to conclude and give space to questions if you ever have them. First observations. Most of the designs that you see nowadays, they are reusing processors and traditional architectures. So that might be good for software compatibility. Imagine that you have an ARM inside the memory, you just have to program the ARM, that's okay. But that's not energy efficient, that's not performance efficient. An important thing is that you have to take care of the power budget because air and power are mandatory in this kind of device, and temperature is a very issue in 3D technologies. And I think the message is that unless you provide some sort of intelligent design, which is also generic in the sense that it can execute any instruction, but also can use the benefit of the memory, you are not going to achieve the sweet spot. So what we've been doing in the past months is pretty much all these ideas here, we already have them in the compiler and in the simulator running. And what we discovered running these things is that you need the compiler to be much more intelligent than you expected. For example, you have a certain bandwidth, but sometimes the bandwidth is not enough. You want to do a speculation. A good example is pointer chasing. If you have a complex data structure, which is, let's say, a graph or something like this, and you have a linked list. So locality, spatial locality is not present anymore. So it really doesn't help to have a huge bandwidth. What you have to do is to read in chunks so that you can speculate whether the pointer is going to be there or not. And we still have to work on the compiler to do this kind of intelligent design by construction. Today, we are using primers. Another aspect is that the simulator is a nightmare. To get a decent answer, it takes hours. Sometimes it takes days. So you really have to think before you launch the experiment because it's really slow. So I'll have to find someone brave enough to check out and do some sampling and some strategy to speed up the information processing that we have here. I think also that sticking with the compiler is quite important. I mean, it's not enough. You need more than that because, as I mentioned, it's very hard for a compiler to say, oh, this is a linked list, so I'm going to use a speculation. I mean, you cannot extract that kind of information. So how can you do this? Well, probably raising the abstraction level, using another language, I don't know. But that's the moment that you clash with the software guys. You will really have to study this and see what you can come up with. And the information I want to pass to you today is basically move information, not data. So looking at the first picture where you spend your time, you notice that sometimes it's in the disk, sometimes in L3, sometimes in the cache. So what I'm thinking to study in the next few years is, okay, we know the stack memory is going to be with us, but the whole reason to have this stacking is about locality. It's about exploiting temporal and spatial locality. And if you think about the kind of algorithms that you are privileging today, the example, the easiest one to understand is about the neural network, pedestrian recognition, for example. We start with a very dense data structure, matrix of pixels, and you do downsampling, and you end up with a different data structure because you want to detect pedestrian or cat or whatever. And you can think of the same thing for voice recognition. You start with a stream, and then you end up with a tree. And so locality of the data is changing. So our message is, for each layer that you're going to have, you have a different bandwidth and a different energy consumption. So whenever you can, transfer, avoid moving data around, and for each layer, provide the specialized pin that can do with this. And of course, not every pin is going to be used for everything, because you need some locality and locality changes during the execution. So only move data when it's needed in the next level. So instead of move data, let's move information. That's the whole idea here. That is going to save energy. And with this, I conclude my talk. Thank you very much for paying attention. If you have any questions, I'll be really glad to answer.
Any questions there? So it seemed to be a lot about what degree of precision of floating point you were going to support, where you ended up, or did I misunderstand the
No, we support floating point.
But it sounded like I'm not 100% sure I understood your slide. I thought that you said that you were going to a lower precision of floating point.
No. We are supporting floating point. What we are doing is that better hardware reuse. So you can do floating point or fixed point, but changing some switches instead of just being massive. But
going to a tensor unit instead of the vector unit or something?
No, yeah.
I'm trying to get some intuition of where the big advance came from.
The big advance, I think, is in the connection with the compiler. I think the big advance is supporting software. So
No, I mean the big advance in energy efficiency.
that I'll have to ask my students. I don't know, but it's in the line of not changing precision. Changing precision is the next study I want to do, but floating point is already an approximation. But at the moment, they are supporting floating point as a regular design.
Other questions? Yeah, sure.
Yeah, thanks, Luigi, for the great talk. So I was kind of wondering that it seems that you are being able to do the vectorization, manipulation, whatever it needs to be done in order to get all the addresses right and then do the access, and you are somehow doing that in the memory, and that's where you get the improvement. Is that?
Yes, yes.
So how do you plan to extend it to non-vectorizable code, or even simply like vectorizable but let's say scatter data kind of operations?
Yeah, I think we know how to do it in hardware. We did by hand, and you say let's try to do pointer chasing. Some kind of real data structure that you have to access. And we written code by hand, and what we inserted was speculation. So instead of bringing a full vector and searching inside the vector, we bring smaller vectors and hope that, that something's going to happen. And we discovered that that's quite effective. We still can provide speed up. But my clue, my view is that there are two problems. The first problem is that probably main memory is not the right place to do that kind of thing. Let me give you an example. If you run C and you allocate memory for a linked list, it's stupid to allocate a single byte at a time. You allocate a bunch of things, and then you have some locality. However, this is a programmer's job. And somehow it's not in our hands. So I think the solution must come somehow by doing something at the programming level that can provide us. On the bright side, if you think about Java, Python, that kind of languages everybody's using, there is a machine which is responsible for memory allocation. So I think that not working at the compiler level, but at the virtual machine level, the answer is going to appear to us. But again, my hope is that you can hide this from programmer, that the programmer can continuously working on his flow. But I don't have the whole answers now. I hope I can convince some poor student guy to work on this kind of thing.
And then another quick question is, the first slide that you were showing, the polybench benchmarks.
Yeah.
Are you running this on a full x86 machine?
Yeah.
So I was kind of wondering that polybench are really like small, really small kernels. And so is it, I was kind of thinking that your results are a little bit skewed in the sense that the code is really small and you are really spending all the time in doing the cold start in some sense.
No, that's a very worry, but we do also have, let's say, full applications like databases. And all the papers we published were about not kernels, but rather full applications. And in the database case, we got a very decent speed up because cache misses were 40%. So I agree. Some of these examples you spend too much time in the beginning, but most of the examples, nowadays you're bringing too much data and have to worry about this thing. So yes, the numbers might be skewed, but on general, for big applications, we see the same behavior too.
Okay. So kind of following on Luca's earlier question, and a statement you made in the beginning about the programmers, making it easy for them. So one of the things that I struggle with enormously is that you know, when you have an operating system between you and right, I mean you're in virtual memory, so when you're in the memory device, you don't even know what a pointer means, right? Yeah.
Look, this is an excellent question. You know why? Because I know the answer. That's fantastic. So the virtual machine is very interesting, and I want to warn this community that most of us, including myself, we have developed accelerators all of our life. And most often we forget about the operating system. And so we say, oh, we're using memory, accessing memory from the processor. Really? Where's the operating system? And that came to us because of this work. So what happened is that we had to build a memory management unit. So we have to own the page tables to understand where the address is going. And that's hidden in this project. I mean, we do have a memory management unit, and the data I'm providing you is after address translation. So yeah, you have to take into account the programmer is willing to use the operating system. We have to deal with that. And actually, after we had the courage to go there and check the memory management unit, we said, it's not that complicated. So we didn't have a TLB inside the memory, inside the 3D stack. We had to have a TLB, just stupid, no? But the good news is, once you understand it, it's easy to do it.
Thank you.
No, thank you.
Thank you very much. So my first, years back when I first saw Team, I said, okay, this is a crayon chip, right? And it kind of, from your data, it kind of looks like that because the simple units work very well and within 1 volt. But the problem is that there's many volts. And the moment you start not fitting in one of them, your data, then you need to communicate. So now you have a full-fledged parallel system. Can you coordinate the communication within processing units between volts?
Yeah, no, wait. Two levels of answers. The first answer is, if I want to read from a position, whenever I remember, and write to another one, there is already hardware to do this inside HMC nowadays. So they have the switches. Notice that we're doing vector operations, not multiple instruction, multiple data operations. So synchronization is our responsibility, and yes, we can. Now, expanding a little bit your question, what's going to happen when several processors are asking the HMC to do these things in parallel to me? I don't have the answer right now. I need other PhD students to check out what's going on. It's a very valid question. At the moment, you have a single processor that says, I want you, memory, to do this thing for me.
So we need to work on the network part.
I'm not sure it's a network part. I really think that the real problem is, again, as in the parallel domain, is deciding who gets the device. And once you give him the device, you do something, and then wait, now I have to go to the other guy, and that's, that's some kind of, I really don't have an approach on how to do that. But I think that the hardware to do that is not the problem. The problem with the synchronization is at upper levels. That's what you have to deal with.
Other questions?
Yeah, maybe the last one. Okay, I'll start a question, from the title of your presentation, but try to change it. Okay, you mentioned, the title has the word guns and bullets. Okay. PIM is a silver bullet.
I think
or just one bullet
No.
to kill. Not to
The idea is that,
So this idea.
yeah, I think the idea is that the bullets should shoot themselves, right? Don't bring the bullets to the machine gun. Let the bullets shoot themselves to where they have to, and you're done with it. And pretty much that's the idea on this. Look, I think the real message is here. So there's no silver bullet. Now coming back to bullets, there's no silver bullet that's going to solve the problem that we have. We need several different approaches and several different layers, and that's good for us researchers. We have more work to do. And what my claim is that maybe the general purpose processor research is sort of saturated. We have to move to other levels. Like Tulika did, very low power, energy efficient, or high power, but data being transformed. This is one aspect. The other aspect is that this whole stack here is based on the idea that the problems that we are facing in software lost their locality properties. And again, I come back to applications like databases, recommendation systems, machine learning stuff. Massive amount of data. Some of this data has no locality, temporal locality. Some of this data has locality. And we built this stack, and you're going to still use it. So for each kind of problem, probably you're going to work on a different level of the stack. Now we have to figure out how to automate this, and how to, because now we'll do it by hand or by specialized compiler. But you want a regular programmer to run Java, and the system, the runtime system, will have to distribute this task in each layer of the stack.
So, thank you, Luigi, for the presentation.